Hello everybody, welcome to the Frequentist A-B testing video in the large-scale machine learning section of ML Expert. So far, we have ingested our data, we have processed that data, we then put orchestrations around the processing of that data, and finally we explored our data and its application to models. When we get to the point in which we want to test a model because it looked promising in some offline evaluation, we want to be able to test that model in production against real users. There's many ways to do this, and in this series we're going to talk about a few of them. The idea is that we start with a hypothesis. The hypothesis allows us to describe how we're going to replace one user experience with another, and how a user will react to those new experiences. For instance, if we have a recommendation algorithm today, which just recommends the most popular piece of content, and we want to introduce some degree of personalization with a machine learning model, then that model would be the new experience that we're replacing with the old recommendation algorithm. These typically involve at some point a UI change to reflect this new experience. However, it can also be not so apparent to users, such as demand forecasting. So let's say that we have some new content being released on a video platform. We could write a model to forecast how much traffic this content will receive, such that we can prepare ourselves and purchase the required hardware to support all of the incoming traffic. This isn't something that would be apparent in the UI, but you would definitely notice if we got it wrong in under-purchased hardware, such that you wouldn't be able to access the content upon its release. Finally, it could even be more subtle. Let's say that we want to have some form of dynamic caching. In that case, a machine learning algorithm would be able to decide what items to cache and what items not to cache, and then we could measure the performance of that algorithm based on the latencies that the customer sees. Now, this wouldn't necessarily be apparent on the UI, but you would definitely notice it in the form of a latency improvement in the case that your ML algorithm actually worked. So after we decide on which experiences we want to replace with new experiences, we also want to decide on what the dependent variables should be. So the dependent variables here could be the incremental revenue or profit lift. It could be the number, rate, or probability of ads being clicked. It could even be the listening or screen time of a particular application. Next up, we want to talk about the directionality of these dependent variables. We want to be very specific in which way these dependent variables will move. As well, we want to anticipate multiple changes. So if we make an assumption that revenue will go up, we also need to make an assumption about what will happen to profit. If we have an algorithm that is lifting revenue, but it's pushing a lot of loss leaders, that's the case where you would have a business loss in terms of selling that item, but you hope that customers purchase another item as well that you can actually make a profit on. So if the ML algorithm is increasing revenue by pushing a bunch of those loss leaders, you also want to be very specific about what will happen to profit. Will it go up, stay flat, or go down? Again, the idea here is to be very specific about which direction each dependent variable will move based on the presence of your new experience. Next up, we want to decide who will actually participate in the experiment. We can have users from some particular country or not particular countries participate. We can also section users out based on their time that they've been with the platform. As well, we can decide which user interfaces will be a part of the experiment. Will we allow the app or just desktop or both? A templatized hypothesis could look like this. If we replace some experience X with some new experience Y for some distinct set of users, again, this would be selecting which users are in the experience, then the metrics A, B, C, or whatever dependent variables that we decided on, will go up or down, respectively, and some invariants won't change. Here, the invariants are something that we must hypothesize will not change based on the replacement of some experience with a new experience. So one way to test out our hypothesis is to use A/B testing. A/B testing usually consists of some control group in which the experience is unchanged. We compare the user's reactions in the control group to a treatment group which has received the new experience. Now, in some cases, this could mean half of the users would be in the control group and the other half would be in the treatment group. If we can measure significant differences between the control and the treatment groups for some changes that we were expecting, We'll then be able to determine if the treatment experience should replace the control experience. Now, in terms of an example, a treatment could be a recommendation algorithm which recommends personalized content, while control could be some existing experience which just recommends the most popular content. If the treatment resulted in more clicks or more revenue, then we could make a business decision to replace the control experience with the treatment experience. So let's say that we have a group of users here, and we send them push notifications. Those are the notifications that appear at the top of your phone when someone messages you or an app wants to let you know of a particular promotion. Now, if you're interested in what the push notification says, you'll often click that push notification to route you to the app. So let's say that we were running an app and we wanted to test out if a new style of push notifications were more effective at getting users to interact with our app. So right now, we have some control experience, and this control experience is such that the push notification is the same for everyone. It just recommends the most popular content. Someone had an idea and said maybe if we personalize these push notifications per customer, then maybe we could increase the rate at which these users will click on the push notifications, increasing the interaction with our app. This would be the treatment that we want to test against control. So the goal here is to figure out if the treatment is better, equal to, or worse than the control. There's several ways to do this, but in this video, we're going to go over the frequentist approach to A/B testing. In terms of being a frequentist, we need to have a baseline. So let's say that we sent out 100 push notifications just recommending the top posts, and let's say that 7% of the users clicked on or interacted with that push notification. So here, our click-through probability would be 7%. The baseline is what the current control experience offers in terms of some metric that we care about, and that's what we want to beat with any new treatment. We also need a minimum detectable change. All this means is that if we're at a 7% click-through probability, we're going to need to beat that 7% by some amount to cover the cost of our experiment. Experimentation isn't free. It can cost time, employee resources, and potentially even new hardware in some cases. So for our example, if we did have that 7% baseline, we could decide that in order to take care of our cost, at a minimum, we need a 1% lift in that click-through probability. That's why it's called the practical significance boundary, because if we get anything lower than that, then it's practically not worth it. Now the next thing that we need is the power. The power is going to be the percent of the time that this minimal detectable change is found, assuming that it exists. It's usually represented by this here, so if you see that later, remember that it's power. We also want the significance. That's the percent of the time that the minimal detectable change is found, assuming that it doesn't exist. This is often represented as alpha. Finally, we need the sample size. The sample size will tell us how big each group, control, and treatment need to be in order to measure some significance or power. Here is the equation to get the sample size of each group. The baseline click-through probability is 7%, so that's P1. The baseline plus minimal detectable change is 8%, that's P2. Alpha is the significance, which is commonly 0.05. And beta is the power, which is often 1 minus 0.8. These are subscripts because they're the z-scores of those particular values. This is here to represent that the alpha's z-score can be measured from a one-tailed or a two-tailed distribution. In our case, since we only want to measure a lift and not a total change, we only need a one-tailed z-score. Now also, in terms of frequentist testing, you'll hear about something called the null hypothesis. This is the case in which our hypothesis is incorrect, such that there's no difference between control and treatment. Usually, you'll hear the terms of either accepting or rejecting the null hypothesis. If we accept the null hypothesis, this means that there is no significant difference between the control and treatment. If we reject the null hypothesis, then that means there is a significant difference between control and treatment. So what does it actually mean to have a significant difference? For instance, if the treatment group measured 8% click-through probability, and the control group measured its regular baseline of the 7% click-through probability, then how do we know that 8 is better than 7? Intuitively, you could think 8 is better than 7 just because it's greater. But we have to remember that this 8% and 7% click-through probabilities came from a sample of the total user population. These are samples because we're only running these experiments for about 2 to 4 weeks, which means not every single customer that we have will go through this experiment, so we have to treat these numbers with uncertainty. So the real question that we want to answer is how likely would an 8% click-through probability have been given that the null hypothesis is true? Remember that the null hypothesis being true would mean that there is no difference between control and treatment. So this is effectively saying how likely would it have been to measure an 8% click-through probability in the treatment group given that there was no significant difference between control and treatment. In the frequentist world, we answer this question by finding the probability of seeing that 1% click-through probability difference, here between 7 and 8, by random chance if we were to run the experiment many times. And we use a p-value to answer this question for us. The p-value is the probability of seeing the result, or a more extreme result, in this case a greater result than that 1% difference, by random chance if we were to run the experiment many times. Typically, we work with a p-value of 0.05. This 0.05 means that if we were to run the experiment 100 times, only 5% of those cases would we have measured that 1% difference in the case that the null hypothesis is true. So let's go through an example here. So we have control as a measured 7% click-through probability. Treatment has a measured click-through probability of 8%, and the number of users which were in control were 1,062, and the number of users that were in the treatment group was 982. Now the reason why we have this variation here is because we're randomly assigning each user to a particular group. So how do we actually calculate the p-value from this information? First, we'll go over the r value here. This will be the click-through probability of control multiplied by the number of participants in control, plus the same for the treatment group, divided by the total number of participants. This r value is 7.48%, and that will be used to calculate the z-value here. So in the numerator, we have the click-through probability of the treatment minus the click-through probability of the control group, so that would just be 1 in the numerator, and we divide by the square root of r times 1 minus r, which we solved for previously, times this expression here. So that gives us a z-value of 0.858. So what do we actually do with this? If we take this value and look it up in the one-tailed z-score table, we'll see that we get a value of 0.1949. This is greater than our p-value requirements of 0.05. What this means is that the differences that we see between the two groups in terms of click-through probability or the number of participants in each experiment group don't create a difference that is statistically significant. Now, if we instead had 10 times the number of participants in the experiment, we'd see that our p-value would be 0.004, which is less than 0.05, which means we could reject the null hypothesis and accept the alternative hypothesis. What this means is that there is a statistically significant difference between the two groups. Now let's say that we had the same number of experiment participants, except this time the click-through probability difference was 3%. Well, in that case, our p-value is also lower than 0.05, which means we could reject the null hypothesis. As well as the p-value, we also want confidence intervals surrounding these click-through probabilities. Because remember, since these click-through probabilities came from a sample of users and not the entire population, we can't say with 100% confidence that these are the exact values. So to calculate our confidence interval, we take our click-through probabilities, which in this case is 7 and 8. Now, since we're only concerned with lifts in the click-through probability and not necessarily just a change, for our confidence interval here, we're actually only going to concern ourselves with the lower bound. So here, if we substitute in a one-tailed z-score at 95%, and as well the control click-through probabilities, then we'll get this here. This is equal to negative 1.28%, which means our confidence interval lower bound for the control group in terms of its click-through probability is 5.72%. For the treatment group, if we plug in those numbers, again, we're still using the one-tailed z-score here, we get 6.58% as a confidence interval lower bound. What this confidence interval lower bound means is that if we were to run the same experiment 100 times, about 95 of those cases, or 95%, would result in a click-through probability of at least these values. Alright, so beyond the A-B testing, we can actually have an AA test. This is when you have a control and a treatment group, but they both receive the same experience. This is a great way to test your A-B testing framework because there shouldn't be statistically significant differences between the two groups. That means this can potentially help verify your A-B testing tool by checking for sample bias. So for instance, our function that randomly assigns users to particular groups is not actually random. This could help us find that out. It will also help us figure out if there's any incorrect analysis going on. Finally, AA tests are helpful when we're working with overly sensitive metrics. So let's say that we have some metric that we want to optimize that has a very high variance. What we can do is AA test that metric and then measure the differences between both of those groups, A, and whatever that difference is, we can assign that to be at least our minimum detectable change. This helps us because now we know that at least that change can happen when we don't even have any differences between control and treatment. Now, just some tips about A-B testing. You generally want to make sure that they run for at least 2 weeks. This will help us observe week-to-week variations if they're there. Now, generally, you have to run the A-B test for as long as it takes to get your required sample size. However, we should consider things can vary from week to week. So generally, A-B tests rely on the assumption that we can extrapolate our results. What this means is that if we run an experiment for 2 weeks and we decide to replace the current control with the new treatment because there was a statistical difference that we hoped for, then we're assuming that the results that we saw during that 2-week period will remain for as long as that treatment is in service. This can be a dangerous assumption in terms of seasonality. If we're running experiments around the holidays, we may want to recognize that these same results may not be achievable throughout the remainder of the year. As well as extrapolating through time, we also extrapolate through the entire population. Since we only ran the experiment for 2 weeks, we only got a sample of all of our users. So we're assuming that the users that weren't sampled outside of the experiment will behave similarly to the users that were sampled. So that's why we're actually extrapolating through time and through population. Now, one thing to look out for during A-B testing is change effects. The first one we'll look at is called the novelty effect. This happens when users use something just because it's new. This effect could be transient, such that if we were to run the experiment for longer, we could see some regression in terms of its positive impact. Now, oppositely, there's something called change aversion. This is what happens when users don't interact with something just because it's new. So in the case where we just run a 2-week experiment, whatever we're experimenting with may not receive a lot of attention, but if we were to run that experiment for longer, we could potentially see more positive impacts. Finally, we want to make sure that we watch out for anything that requires time-intensive feedback. For instance, let's say we worked for a university and they wanted us to develop a recommendation algorithm in order to recommend students particular courses. If we wanted to measure increased class attendance, that might be a good thing to measure in an A-B test. However, if we wanted to measure graduation rate, this would likely be a bad metric because at least for the incoming class, 4 years would have to pass before we got any sort of feedback. Since this is so time intensive, invariance could be introduced along these 4 years that could completely counteract or make the recommendation algorithm itself, in terms of courses, completely irrelevant. Now, it depends on your problem, but generally feedback within a month is a good idea. So now let's go ahead and take a look at some of the infrastructure that we'll need to run an A-B test. Here we have our user, here's our application, and here's some user allocator which will manage the A-B test for us. How do we actually represent a user in an A-B test? Now, there's several options that we have. We could store a cookie in the user's browser which indicates to our site which experiment group that the user is in. We could also assign the user ID to a particular experiment group. We could assign a device ID to an experiment group. However, device IDs aren't available on desktops. And finally, we could use our IP address. Generally, we want to pick something that has the least chance of changing during our A-B test. If something is very likely to change across many customers within an A-B test, then it could invalidate our results. In terms of cookies, these will only change if a user resets their browser cookies. The user ID will likely never change. Now, the device ID doesn't change, but this doesn't mean that the same user could log in to another device and receive a different experience, which could cause some confusion. And finally, the IP address is typically less reliable. Alright, so back to our diagram that we have here. So our user will call out to the app for the home page. The app will call the user allocator to get the allocation in which this user should be assigned to either group A or B. The user allocator here will generate an ID for the user. So in this instance, we don't require users to log on, which means we're going to put a cookie in their browser, and the user allocator should generate this cookie for us. So here, we should put this ID in the cookie and assign that cookie to this group. Alright, so we return to this user homepage A because they are now in the A group, and we make sure to equip their browser with that cookie. We do that so that the next time that they make a request to our app, that browser will send the cookie to our application, and our application will call the allocator with that ID. The ID will be returned along with its allocation. That means that this user will get the same experience that they got last time. If we didn't do this, the user could get a different homepage, and this could cause some confusion. Now, for some improved efficiencies, we can cache what users are in which groups, and also the user allocator may want to manage several experiments at a single time. This means that it'll often require an experiment ID as well as the cookie. The experiment ID will represent a specific experiment for which this user is assigned. That means this user could be a part of many experiments at one time. Now, this user gets assigned homepage A. And for this particular experiment, the hypothesis is that if we show users a different home page, we'll increase the number of purchases that they make on our website. So let's say that we show this user homepage A, and sometime later, this purchase happens. This could be on the order of seconds, minutes, or perhaps even days. This is for you to decide. And the user allocator, or some separate service if we want to, will record the action of this particular cookie performing a particular action, which was purchase. Now, obviously, this could happen asynchronously to actually vending the purchase for a user because it's not a critical path. Finally, the user allocator will store in a database the action that this user took, as well as the group that the user was in, and that database will then have some ingestion process attached to it, which we talked about earlier in the series. This could lead into an HDFS cluster. One of the records in the HDFS cluster would look something like this. So we would have the experiment ID, the user ID, or the cookie that we put in their browser. We would detail what allocation they were and what action they took. This would either be a purchase action or a no purchase action if they didn't eventually purchase an item after seeing that home page. Next, we would do some data processing on these records such that we would be able to count all of the page views that all of the group A had and group B had, as well as the number of purchases that groups A and B did. After we have this data, we could have yet another processing step, which would use these counts here to calculate the p-value, the click-through probabilities, and perhaps even the confidence intervals of those click-through probabilities. This information could be propagated to some web interface such that people can go on and monitor, track, and see the history of all of their experiments. So what tools can we use to help us do A/B testing? Well, Optimizely is an option, so is Google Optimize, as well as Facebook Planout. Now, if you want, you don't have to use any of these, and you could implement A/B testing from scratch. So to wrap up, this video covered frequentist A/B testing as a way to measure the differences between ML algorithms that you propose to replace existing experiences. That concludes the frequentist A/B testing video in the large-scale machine learning section of ML Expert. Thanks for joining.